Hello, and welcome to this online session of the Lagrange Science Fair for 2025, where we will be hosting a panel of selected guests for talks revolving around the latest innovation in the ZK domain. Our cryptography at Yale University, and the chief scientist at Lagrange. He will be presenting his latest paper about the dynamic ZK-SNARKs. Babis, the stage is yours now.
Hello, everybody. My name is Papamanthou. I'm I'm very excited to be talking today about some of the latest research we have been doing at Lagrange on dynamic SNARKs. This joint work with Wei Wang, Srinivas, and Dimitris Papadopoulos. So the motivation is, of course, the central thing that we'll be working on at Lagrange, which is zero-knowledge proofs. And we examined a different aspect of the problem of zero-knowledge proofs. In particular, we are asking the question, what happens when you have a proof that has been already being computed with a zero-knowledge proof system, and you want to slightly change the public statement and the witness, or the witness. Okay, so say, for example, 3 wires are changing or 5 wires are changing, leading to a statement that it's still in the language. Now, if you want to update the proof, up to this point, the only way you could do that is to run the prover from scratch, spending linear time, even if the change is very small. In this project, we design new zero-knowledge proof systems that have the property of updatability. In other words, we can update the zero-knowledge proof in time that is proportional to the delta between the old statement, the old state of the wires, and the new state of the wires. And we propose a new notion that we call dynamic ZK-SNARKs, and you can think about it as data structures for zero-knowledge proofs. Okay, so in this work, we have proposed 2 constructions. One is Dynaverse, and the other one is Dynalog. And here we give the table of our main results. We compare our 2 constructions with growth 16 proof system, and as you can see, the update time of growth 16 is n times log n, linear time, whereas the update time of Dynaverse is k times square root of n log n, where k is the number of wires that are changing. The verification of proof size is constant. And then we have another construction that achieves logarithmic update time. In particular, the Dynalog construction achieves k times log cube update time for the proof, where k again is the number of wires that are changing. Verification time and proof size is logarithmic. And we can also make this verify and proof size constant by doing one level of recursion only. So I would like to mention a few things about the core building block of our construction, which is Dynamo. So Dynamo is a ZK-SNARK, a custom ZK-SNARK that we design. It's not a dynamic ZK-SNARK, it's a custom ZK-SNARK that we design for what we call a relaxed permutation relation. So what is a relaxed permutation relation? A permutation relation, when you design a proof system for permutation relation, you have a commitment to a vector, you have a commitment to a permutation, and the proof system for a permutation relation will provide a proof that the elements of the vector satisfy a certain relation with respect to this permutation. For example, z of I equals z of sigma I. And as we know, this is extremely important for proving arbitrary computations, okay? Now, we extend this notion to what we call a relaxed permutation relation, where we prove that z of I equals z of sigma I times hi. So we relax the equality. And this is important. Why? Because the main notion of dynamic ZK-SNARKs is based on this idea of decomposing the witness vector and using individual relaxed permutation arguments for the decomposed vectors. So for example, if we can express the witness vector as sum of zi's, okay, we can provide proofs for individual relaxed permutation proofs for the individual zi's, right? And then we can additionally check that the hi is the relaxation of its vector sum to 0. Why this is good? This is good because then when we change a single element of the vector, we don't have, due to this decomposition, we don't have to touch all the elements of the vector. And this allows us, this primitive of relaxed permutation relation and the notion of decomposition of permutation allows us to eventually get what we want. We apply this decomposition of permutation relations in both our approaches, in both Dynaverse and Dynalog. In Dynaverse, we applied at the level of square root of n buckets, leading to the square root of n update time. And for Dynalog, we apply this notion of a permutation, relaxed permutation relation at this this like LSM tree based data structure, where basically you have levels of exponentially increasing sizes. And by applying this, we're able to go down to log n. This is one part of our construction. Unfortunately, I don't have time to explain all of it. Looking forward to SBC, where Weiji will be presenting all of this. And right, so super excited about this work. I just want to spend some time talking about applications. So the main application that this work was motivated from came from the first product that Lagrange put out, which was the ZK processor. And the idea was that we wanted to maintain proofs of computation, in particular of SQL computations, while blockchain blocks are being produced. So if you have an SQL query, a proof for an SQL query on block I, and then you have a few elements, a few data items that are changing for block I plus 1, we wanted to maintain this SQL proof without having to recompute this proof from scratch, in particular, since the delta from block I to block I plus 1 is very small. So that was what motivated this question. The question is how you can very fast update this proof, right? And before dynamic snark, we only had to do that in linear time. Okay, so right, other applications include, for example, we have another application which is this bounded step incremental verifiable computation, where we show that dynamic snarks can give you a form of incremental verifiable computation for that bounded number of iterations without using recursion, without using recursive snarks, which, as we all know, introduce a bunch of security issues. Other applications include digest translation and updating ML inference proofs. Okay, again, super excited about this work and looking forward to Wedge's talk. Unfortunately, I won't be able to be there, but looking forward to Wedge's talk and disseminating this work more broadly. Thank you.
Thank you very much. So I will be presenting the next session, where we will be talking about another paper that is coming out of the Lagrange cryptography lab, which is which is a paper called Reckle Tree, where we propose a new way of basically storing vector commitments and possibly executing computation on them. So let us start with a little return to the fundamentals. What exactly is a vector commitment? So a vector commitment is, in a trustless context, a way for an actor to commit to an ordered set of values And so to say at position I of the vector, you have the value xi, and I can prove it. This allows the creation of what are basically key value databases in a trustless environment. On a typical application is the Ethereum state tree, where every single contract has a linear storage space that is handled like a key value database, where you have for a given address a given value. And this state is shared and proved at every single update between all of the actors of the Ethereum network. So this is, of course, a bit of a simplification, but you get the idea of why vector commitments are really useful in the domain. So the most common implementation, at least in the crypto world, of the vector commitment are the Merkle tree. So a Merkle tree is basically you take the linear representation of your address space or your vector, and then you will recursively create nodes above it to create a tree structure that is encompassing the whole vector. And then to prove that the vector is actually what you pretend the vector is, you will have a recursively computed set of hashes going from the leaves up to the top, where you will aggregate first the hash of the value here. So you see x1 and x2, so those are the hash of these values. Then you are combining these two hashes from x1, x2, x3, x4 to go to this one. So you can see that here you have this hash, and here you have this hash, and so on, up to the root of the tree. So this is a quite simple case where we have a binary tree and so on, but let's say that the fundamental principles are remaining the same. So in the end, you read this H0 hash, which is at the very top of the tree that we call the root hash. And by having such a construction, you are sure that you can ensure the integrity of your vector. Now, the thing is that typically you want to update these databases, right? Because having a data structure that is committed to, but you cannot modify or insert any value is not really useful. So what you do here to update a value is that you take the value that you change, and you will trace its path from the leaf of the tree up to the root of the tree, and you will update the hashes along this path, right? So this is what you will do as a prover. And then to prove that your proof is correct, what you need to do when you broadcast this modification to the vector to other participants in the network is to provide them the value on the hashes that you meet along this path. So what the verifier will see is that they will see your new value for x2, for HLL, for HL, and for H0. So this is a log n sized proof, n being the number of leaves in the tree. And the verifier already knows this value and this value. And what they will do is that they will compute the new hash. So they already knew x1, so they will, they already knew HLR, so they will compute HL prime coming from your HLR prime, and so on, and so on, and so on. And they will check that in the end, when they recompute everything, they find a new H0 that is actually the same as the one you provided. And if you didn't cheat on the way, the verifier can be sure that your proof here is actually reflective of the update of the x2 value in the tree. Now, the thing is that typically you want to update multiple values at the same time, right? Because there is really very few cases where you have such a simplistic use case that you will only be updating one value. So to update k elements instead of just one, you basically repeat the operation over all of the passes. So here we are changing these 4 elements instead of a single one. And in orange, you can see the passes from these elements to the root of the tree. And in orange, the nodes, the values that the prover will have to broadcast to all of the other participants in the network to ensure that they can actually verify and check and validate the modification of the tree. So now we have a proof size that is in k log n, where k is the number of elements that you want to change, and n is basically the width of the tree. So the good thing with that is that the computation for the validation of the proof is very fast, and the bad thing with that is that the proof size is quite big. So what we are going to do here is to propose a solution where we can drastically reduce the proof size and make it in a basically constant, while maintaining this capacity of performing the computation in parallel that allows for fast proving and fast verification. So we are going to do on a bit of a tangent and start talking about SNARKs. So what is a SNARK? A SNARK is the acronym for a succinct, non-interactive argument of knowledge. So let us take that apart. Succinct means that the proof size are small with regard to the computation that they are proving. Non-interactive means that there is an asynchronous proving and verification process. So basically, the prover is doing its stuff on his side, then creating some proof, and the verifier can verify the proof without having to talk with the prover. An argument of knowledge is, to put it in a very, very big nutshell, a reasonably safe proof of a given computation. So this is, of course, an oversimplification of the whole cryptographic aspect of things, but you get the gist of the idea. So a SNARK is providing two functions. So you have a proving function that is taking the prover key, the witness, and the and the input and providing a proof. And then you can also verify when you have the statement on the proof on the verifier key, whether the proof is actually correct or not. So this the prover and verifier key, you basically only need they are constant values when they have been computed once, so they are not really interesting here in terms of complexity. The statement depends on the problem, and here we have the proof, which is succinct, so very small. So now there have been a development on top of the SNARKs, which are the recursive SNARKs. So people observe that one of the big flaws with SNARK was that computation must be done over inputs of non-fixed size. So it means that you cannot really do stuff like loops or iterations or recursion and so on and so on. And in our very specific case, we cannot really use a SNARK to prove a Merkle tree because the size of the tree will typically be changing, right? Or you would just have to have a proof for a gigantic tree, but then the performances would be absolutely awful, and you would have an upper bound on the side of your tree, which is not very good. So what has been developed are recursive SNARKs. So recursive SNARK basically introduce a recursion step in the whole idea, because now the proving function can also take a proof of a previous computation and generate a proof prime that is proving that not only the computation over the statement on the witness is correct, but the proof from the previous layer of the previous iteration is also correct. And in the end, you just need to have one proof pi prime to verify both the pi prime and the pi proof. So you are basically killing two birds with a single stone. And given that you can iterate without any practical limitation on the number of iterations, outside of computation limitation, of course, it means that you can really handle arbitrary sizes as long as you have circuits that are handling the condition for the iteration start and end. So the idea here is that now we are going to take to go back to our Merkle trees, but on top of the hashes, for every single node, we are also going to store a proof, right? And what we're doing is that this proof, to put it in a very simple nutshell, will be validating the hash computation for this step. So this means that now when we want to store stuff, we are going to generate HLL and we are going to generate the proof for that computation. Then we are going to generate this one from these two here and here, and we are going to generate a proof of the truthness of the computation for this hash from the previous hashes, and so on and so on and so on, up to the root hash of the tree, where we will generate for the computation of the root hash of the tree a pi0 proof that will be recursively embedding not only the computation of H0 but also the validity of pi L and pi R. The computation for pi L, will itself include the validation of the computation for pi LL and pi LR, and so on and so on and so on. And in the end, the good thing is that with a single proof, you will be able to prove to a verifier, so with a proof size in O1, you will be able to prove to a verifier that the whole computation is correct, even though you don't really need to have a tree of a fixed size. Typically, you will cache on the prover side the intermediate proof because when you want to update the tree, it's better to already have them computed if you don't need to recompute them. And same thing, you are going to cache the hashes just for computational purposes, but you could definitely do it from scratch. So now let us look like to the process, to what the process would look like for updating one element. So the computation of the hashes will be exactly the same. So we start from the element and we go up to the root of the tree. But now what we are going to do on top of updating the hashes is that we will be computing this updated intermediary proof here and there, right? But in the end, when we want to prove the validity of the insertion of the value to the other participant in the network, we are only going to send them pi0 on some ancillary data, but that are basically of constant size. So now we can update one element with a proof that is not depending on the depth of the tree. And if we extend the ID to k elements, so we are still going to follow the passes from the elements to the root of the tree. But basically, now we are only going to send the final proof. So even if we update, like in this case, 3 elements, or in generic cases, k elements, we are still going to have a proof that is basically in constant size. So this is a huge improvement over the size complexity of the proof in the previous case that was in k log n. So there is also something that we observe is that in Merkle trees, we only aggregate hashes, right? So we have these hashes that are propagated from the leaf up to the root. But in Reckle trees, we aggregate hashes on proofs. For now, I only talked about proofs as they were proving the computation of the hashes that is aggregated up to the top of the tree, right? But what if we extended the circuit that is proved by these proofs to compute something more than just the aggregation of hashes, right? So let us take this example where we have a function f and a function r. So this is basically the basic setup for a map-reduced environments, right? So you have a function that you map over all the leaves of the tree. And then as you go up the tree, you will apply the reduce function to take these two values and turning them into one. Same thing here. Then you will reduce these two values into a single one, then these two values into a single one, blah, 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 up to the very root of the tree where you will have the final result of the MapReduce computation. This is a very flexible computation framework that can encode a lot of different operations. So if we take an example here, we would have FLL, that is the reduce of fx1 on fx2. Then we are going to take FLL, FLR, reduce them together and get FL. And then we are going to get FL on FR, reduce them together and get the final F. So if we do that, and if we have a computation definition for R on F that is actually encodable in a SNARK, in a recursive SNARK, then we can basically encode every single MapReduce operation over a tree, compute it and prove it, all of that in a constant size of proofs. So this is basically the idea behind the Reckle plus trees. And if we were to have a very short abstract about their pro and their cons, so the pro are of course feature parity with Merkle trees. Not only do we have the same features as Merkle trees, but we can do more things. We can prove any MapReduce computation that is expressible within a SNARK framework. And the proof size is constant for all of these operations. On top of that, given that the scheme is quite generic, any SNARK can be used, so there is no hard tie to a peculiar implementation of the SNARKs. The cons, of course, are this is something that is much more complex to implement, and that might be a bit overkill for your needs, and that proof computation, so ZK proof on SNARK are quite infamously compute heavy and very expensive to compute compared to, let's say, a native arithmetic operation in computers. But given the improvements of the performances in the ZK world in general, we can hope for this to become less and less an obstacle as the time go by. Hey, so now is the turn for Trisha, who is currently a PhD student at Stanford, and she will be giving us a talk about a new kind of vector range proof. So Trisha, thank you for being there, and the floor is yours.
Can you see my slideshow?
Yes, perfectly fine.
Great, perfect, thank you. So thank you. My name is Trisha, and today I'm going to be talking about Descartes proof, efficient vector zero-knowledge range proofs, and their applications. And this is joint work with Dan Bonet, Rex Fernando, Kamila Nazarkhanova, and Aline Temescu. So this presentation is going to be about the development of a new zero-knowledge range proof, or a ZK-RP. And so first what I'm going to do is explain what ZK-RP is at a high level. And on the next slide, I'm going to give some examples of blockchain applications for ZK-RPs. So As in any type of proof system, we have a prover and a verifier. The prover is going to have access to a vector. We'll call it Z1 through Zm. And you can think of the elements of this vector as field elements. So basically just, numbers from 0 to p minus 1, where p is a prime. The verifier is going to have a commitment to this vector. So commitments, we kind of think of them as the cryptographic analog to physical envelopes. So you have this vector commitment, which basically means that there is a vector inside of this sealed digital envelope. And so the verifier can't see what's inside because it's sealed. But conversely, because it's sealed, the prover can't change which vector is inside. So there is only one vector inside, and the verifier doesn't know what that vector is. So what the prover wants to do in a zero-knowledge range proof is it wants to provide a proof pi that can be checked against this vector commitment. And this proof pi should prove that all of the elements in the vector are in some range 0 to n without revealing anything else. So that second part, though, without revealing anything else, that's the zero knowledge part. So basically, once the verifier verifies this proof, what they're going to learn is that all of the elements in the vector are in a range, but they're not going to know which elements in the range this vector corresponds to. Okay, so now that I've explained at a high level what this is, let's talk about some blockchain use applications. So one really important use case for ZK-RPs is publicly verifiable secret sharing schemes for field elements. So let's kind of break down what that is. A field element, again, you can just think of this as a number from 0 to p minus 1. A secret sharing scheme is basically where you have some kind of secret, so also a field element, some number, and you want it to give a bunch of different parties shares such that if t of them come together, they can reconstruct the secret. But if any less than or any fewer than t of them come together, they can't reconstruct the secret and they won't learn anything about the secret. And then the publicly verifiable part basically means that you have a system where someone can publish a list of encrypted secret shares, and they can provide a proof that these encrypted shares actually do correspond to a legitimate secret sharing. And what legitimate means depends on the actual scheme. And you might wonder, well, why are these things useful? And so we actually did this work at Aptos as interns last summer, and basically having this kind of scheme would enable on-chain threshold cryptography for them. So that at a very high level, that's kind of why we want something like this. And the reason why something like this requires a zero-knowledge range proof is often these schemes, the encryption scheme that they use is El-Gamal encryption for field elements. And the thing about El-Gamal encryption for field elements is that decryption can only occur when the encrypted plaintext is actually quite small. Okay, so remember I said that the publicly verifiable part of publicly verifiable secret sharing schemes is that we need to be able to prove that these secret sharings are legitimate. So if you're using El-Gamal encryption, part of proving that your PVSS transcript is legitimate is proving that the El-Gamal encrypted shares are actually decryptable. And how do we prove that? We have to prove that they're within a certain range, okay? But of course, we don't want to reveal anything about what the plain text actually are, so that's why we need a zero-knowledge range proof to prove that these shares are decryptable. And some other applications, confidential transactions, you might want to prove that your balance is above a certain threshold for some kind of purchase. Also with electronic voting, you might want to prove that a bunch of different values are either 0 or 1 and nothing else, so things like that. And kind of an important thing is that for this PVSS use case, the range size that we'd be dealing with is 2 to the 40. And that range size is really important when considering alternatives in prior work. So before I get into our construction, I just want to talk a little bit about what else has been done in this space. And for this slide, you can think of it as we are trying to prove that m values are in a range 0 through n. And so there's a class of prior work called lookup arguments. These are things like CQ and lasso. And these have very fast prover time. Unfortunately, for some of these schemes like CQ, the prover must store a hint that is linear in the size of the range, so O of n. And again, that's going to be a problem for us in our PVSS application because our n is 2 to the 40. And so asking provers to store a hint that is O of 2 to the 40 is going to be practically infeasible. Additionally, some of the schemes like Lasso are not designed with zero knowledge, and kind of adding zero knowledge is non-trivial and could increase costs. Another type of zero-knowledge range proof is bullet proofs, and they have a really small proof size, a really fast prover. Unfortunately, their verifier is going to be linear in the number of values you're proving in the range, so that would be O of M. And there's also this prior work called missile proof, which has a really small proof size, really fast verifier, but a kind of at the expense of a slightly slower prover. And so our work, Descartes proof, what it does is it kind of just improves on all of this prior work in at least one dimension. So we don't have this linear size hint. We do have a logarithmically sized SRS, but that's kind of, a lot of these schemes will have that due to the commitment. It's also provably zero knowledge. It has a faster verifier than bulletproof, so it's going to be logarithmic in the number of values and size of the range. And it also has a faster prover than missile proof, both asymptotically and concretely for ranges that we care about. Okay, so before I describe our zero knowledge range proof, let me kind of just state a little bit more formally what we want. So we need a proof system for the following relation. So the instance, the public statement, is going to be some commitment, and the secret witness is going to be some vector, some M element vector. And what we want is for this commitment to be a vector commitment to this vector, and we want the vector to have all values, all of its elements should be in the range 0 to n. And since the proof system, we need three qualities or properties. The first is completeness. This basically means if an honest prover is trying to prove this about an instance witness pair that is actually in the relation, then they should succeed. We also want soundness, which means that if a dishonest prover is trying to prove that some instance witness pair that is not in the relation is in the relation, then they should fail. And this is again with overwhelming probability. And then the last property is we want zero knowledge. So what this means for us is that the verifier should only learn that the elements of V are in 0 to n, but it shouldn't learn which elements V actually contains. Okay. So now I'll get into a little bit of the design of our ZK-RP. So this slide should look very familiar. It's the one I had up at the beginning. Kind of shows the general high-level overview of a zero-knowledge range proof. And when we're designing a zero-knowledge range proof, we kind of have two levers to pull at. The first is the vector commitment scheme. So what we want to do is we want to choose some kind of commitment scheme that actually helps us in designing an efficient proof. And then once we have this commitment scheme, we want to actually design the proof with respect to this commitment scheme. So first, I'll talk about the commitment scheme, and what we're actually going to use is a polynomial commitment scheme. So I'm just going to quickly go over what a polynomial commitment scheme is. So it basically allows a prover to commit to a polynomial and then prove its evaluations at certain points. So you have a prover and a verifier. The prover has some polynomial. I've represented it as a mu-variate polynomial because we are going to be dealing with multivariates later. And what the prover can do is send a commitment to verifier. So again, that's basically stuffing this polynomial f into a digital envelope, digital sealed envelope. The verifier can then make a point query, which is, so here the verifier is basically asking, what is f of x? And the prover can send back a proof pi and a claimed evaluation y. And basically, if this proof pi verifies, then the verifier will be convinced that f of x is equal to y. Importantly, some polynomial commitment schemes are homomorphic, and that basically just means that if you have a commitment, if you sum the commitments to two polynomials, you get a commitment to their sum. And again, why is this useful? Well, what we're going to do is, I said we needed a vector commitment, and what we can do is we can actually encode vectors as polynomials, and then just use a polynomial commitment scheme as our vector commitment scheme. All right, so to see how we use this, we're going to start off with a range proof from Bourgeot for a single value. Okay, so basically what we're going to do is we're going to show this range proof for a single value, and then our work is adapting this to a batch setting in an efficient way. So in Bourgeot's range proof, the prover has a single value z in 0 to n, and the verifier has a commitment, okay? And this commitment is going to be a homomorphic commitment to a univariate polynomial encoding of z. So basically what that means is we're going to somehow encode z as a univariate polynomial, and then we're going to use a homomorphic commitment scheme to commit this to this polynomial, and that is what is contained in this commitment that the verifier has. And the prover, again, just wants to send a proof pi to show that z is in 0 to n. Okay, so how do we do this? Well, basically, the intuition is that to prove that z is in 0 to n, you want to prove that z can be represented as log n bits. Okay, so what the prover does is it basically sends commitments to polynomial encodings of every bit of z. Okay, so the verifier is going to end up with log n additional commitments, and com1, for instance, is going to be a commitment to the univariate polynomial encoding of the first bit of z. Okay, so take the first bit of z, encode it as a univariate polynomial in the same way that we encoded z as a univariate polynomial in this first commitment here, and then commit to this encoding. And we're going to do that log n times for each bit of z. So now, in order to actually prove that z, whatever is committed to in this first commitment, is comprised of the bits committed to in these next log n commitments, the prover has to show two things. So first, it has to show that each of these commitments that was sent over, these log n commitments, is actually a commitment to 0 or 1. And then secondly, it has to show that the bits in these commitments sum up to z. And I have sum in quotation marks because it's kind of a weighted sum. You have to multiply it by 2 to the j minus 1. All right. So this first thing we can do with a zero knowledge zero check for univariate polynomials. And this is going to be done using the evaluation function for polynomial commitment schemes. And then the second thing, the verifier can just check using the homomorphism of the PCS. So basically, we kind of want to check this linear relation between the z's and the bits of z. And to do that, we can just check the linear combination between these commitments. Okay. So this scheme is complete, sound, and zero knowledge. So those are all the three properties that we want. Unfortunately, it's a little bit inefficient. And the reason why is for every value z, we're sending over log n commitments. So if we were to kind of naively scale this up to m values, we would have to send m log n commitments, which just is not going to be really what we want efficiency-wise. And so how do we address this? So how do we somehow take this scheme for proving that a single value is in a range in zero knowledge and somehow expand it to multiple values? So how do we batch this scheme? So again, the inefficiency in the single value scheme is that each commitment only encodes a single value, right? So how do we address this? Well, we're just going to kind of do the obvious thing. We're going to encode more than one value in each commitment. And the cool part is because of the commitment scheme that we're using, the commitment size does not actually depend on the number of encoded values. So the proof size ends up being the same no matter how many values we're trying to prove are in the range. Okay, and so how do we actually encode more than one value? Well, what we're going to do is we're going to replace univariate polynomials with multilinear polynomials. And this is not necessary. You could do this. You could encode more than one value using univariate polynomials, but the advantage of using multilinear polynomials is that we're going to get a prover time savings. And that's actually how we end up doing better than missile proof. And if you're not familiar with multilinear polynomials, they are just multivariate polynomials where every variable has degree at most 1. Okay, so now I'm going to show you how we batch Bourgeois range proof, and the things that are different, I'm going to show them in red. So instead of having a single value, we're going to have this vector of values. And instead of having a commitment to a univariate polynomial encoding of a single value, we have a commitment to a multilinear polynomial encoding of the vector of values. And again, we want to send some proof pi. And so now what we're going to do is instead of sending log n commitments for each commitment commits to a single bit, we're basically going to send log n commitments where each commitment commits to a vector of bits. Okay, so you're still going to have log n commitments, but this first commitment com1, it's going to basically be a multilinear polynomial encoding, or a commitment to a multilinear polynomial encoding of a vector of the first bits of all of the elements in Z. Okay, and so then the next commitment is going to be a commitment to the second bits of all of the elements in Z, and so on and so forth. And then the two things that the prover needs to prove are very similar. So first, it needs to show that the vectors that are committed to in these log n commitments are actually vectors values of only 0 or 1. And then it needs to show that these vectors of bits in each commitment kind of sum up to the vectors E. And again, sum is in quotations, is going to be a weighted sum. So just like in the single value case, the first one can be done with a zero knowledge, zero check for multilinear polynomials. And the second one can, again, if we're using a homomorphic multilinear commitment scheme, we can just use the homomorphism of the polynomial commitment scheme. So the second one is pretty easy. It's kind of exactly the same thing as in the single value case. This first one is a little trickier. And the reason why is because we need the zero knowledge, zero check for multilinear polynomials. So it turns out that we can do a zero check, for multilinear polynomials using sum check. The problem is sum check, kind of in its initial design, is not zero knowledge. And there are several zero knowledge sum check constructions in the literature, but they're either not entirely efficient or they're not fully zero knowledge. And we really want a fully zero knowledge solution. So what did we do? We designed our own zero knowledge sum check. And to prove its security, we introduced a new information theoretic proof called homomorphic polynomial interactive oracle proofs. And if you're curious to know the details about these last two parts of our work, then you can see the paper, or you can come and check out my talk at SBC. Thank you.
Thank you very much. So, hello. So next talk will be done by Alireza Shirzad, who is currently a research intern at Lagrange, and he is a PhD student at UPenn, and he will be presenting a new family of ZK-SNARK schemes. Alireza, the mic is yours.
Yeah, thank you for the introduction. Yeah, I'm going to present Garuda and Pari, our two recent SNARK constructions. This is joint work with Trisha and Michael. So let me first define SNARKs. SNARKs are succinct non-interactive arguments of knowledge. Usually two parties involved, prover and a verifier. The prover knows a witness that satisfies a function, f of x and w equals 1. And there's usually a setup phase beforehand, where the proving key and the verification key is passed on to the prover and the verifier. And then the prover, upon having the witness and the instance and the proven key, will send the proof string to the verifier, and the verifier having the verification key and the public instance will either accept or reject. And this protocol should be complete, meaning that if P actually knows a valid witness, then the verifier has to accept the proof pi. And it should be knowledge sound, meaning that if P does not know a valid witness, then V has to reject pi. Then V has to reject the proof pi. And it should be succinct, meaning that the proof size and the verification time should be sublinear in the size of the witness and the computation. So SNARKs seem to be magical constructions that somehow compress the computation. A natural question is that how small can the proof size be? So aside from the theoretical curiosity, for blockchains, it actually matters in practice. The smaller the proof size, the less gas costs we have to pay to post these proofs on chain. So Gross at 2016 showed that for GGM-based SNARKs, there's a lower bound on the size of the proof, which is two group elements. Essentially, in 128 bits of security is 144 bytes. And he himself constructed a SNARK, which is a celebrated Gross 16 construction, and it's three group elements, 192 bytes. And you can see the gap between the lower bound and the actual construction here. So in 2024, Polymath was out. Helger Lipma showed that if we use a random oracle model, we can reduce the proof size to 176 bytes, which is three group elements and one field element. So the question is, can we go lower than 176 bytes? This is the first question that we ask in the paper. And the second question, and that is kind of on the spotlight in recent years in both theory and practice of SNARKs, is that how can we reduce the proving overhead? The proving time of SNARKs has a very, very large overhead, almost up to 1,000 times over the native computation. So the question is, how can we reduce this cost? So I introduce two approaches. One approach is using free addition gates. So this approach means that you only pay cryptographically for multiplication gates, for nonlinear operations in the circuit. And this is naturally achieved by some old school SNARKs like Pinocchio, BCTV14, Gross16. And the other approach that I introduced here is the custom gates. Custom gates are gates that are specialized for repetitive and very complex operations that are going to be encoded as field arithmetics. Like, for example, elliptic curve additions, non-native field arithmetics, high-degree gates that are usually used in hash functions like S boxes and stuff. So this approach was proposed in TurboPlonk and is widely used in industry these days. So the question that we ask in this paper is that, can we have both of these approaches in one SNARK? Can we have both of these techniques for reducing the proving time? Unfortunately, no existing SNARK supports both. So can we achieve this? So our contributions are twofold. We construct Garuda and Pari, two different SNARKs. Pari is the smallest known SNARK with the proof size of only 2 group elements and 2 field elements, which means that concretely is 160 bytes in 128 bits of security, smaller than Polymath, very close to the lower bound of SNARK, to the lower bound of Gross 16. However, note that this lower bound is for GGM. We're using ROM. We're kind of bypassing this lower bound. Okay, so these are kind of incomparable, but that's just, these two numbers are there just for comparison. And we also construct Garuda, the first SNARK that simultaneously supports free linear gates and custom gates. You can see this plot here that we kind of have the fastest proving time. I will elaborate more on this plot in the evaluation section, but just very briefly, we have 3x faster proving time than Gross 16, which only supports free linear gate and does not support custom gates. And we have 2 times faster proving time than Hyperplonk, which only uses custom gates and does not support free linear gates. So we achieve best of both worlds, and we anticipate a better number in proving time. And both of our constructions, Pari and Garuda, use random Merkle model and AGM, algebraic group model. And both are, unfortunately, circuit-specific. Okay, so the new methodology that we use is not that new. It is just the continuation of the work like Spartan, Marlin, Plonk, Hyperplonk. We use an information theoretic part, and we compile it with a cryptographic commitment scheme. However, here, our information theoretic part is PIOP, but our PC scheme is an EPC scheme, is an Equifficient polynomial commitment scheme. I will elaborate on the word Equifficient. Yeah, and this compiler gives us a preprocessing SNARK for R1CS. Okay, so the takeaway here is that our PIOP has fewer responsibilities here, only needs to be sound, and it just kind of checks the nonlinear conditions in our circuit. But our EPC scheme has more responsibility. It's not just the PC scheme, it also checks the linear relations in our circuit. I will elaborate more on this methodology in the future slides. Okay, so our core technique is devising a new link check, a new linear check. So prior PIOP-based SNARKs for R1CS, for example, Spartan and Marlin, they kind of decompose to 2 checks, linear checks and nonlinear checks. Okay, and the R1CS definition is up there just for refreshing your minds. So the nonlinear checks the actual Hadamard product, whether ZA Hadamard ZB is equal to ZC. This is a Hadamard relation over 3 vectors. And the linear check actually checks that the 3 vectors that we provided, ZA, ZB, ZC, actually relate to the extended witness vector, which is Z, by 3 matrices A, B, and C. So these are actually following the A, Z, B, Z, C, Z linear relations. Okay, so the nonlinear check is usually very simple. It's you can just prove it with just 4 group elements and just one simple 0 check, and that's it. So the row check is usually easy. But the linear check, to argue that ZA is actually the multiplication of A times some Z, and I know that Z, and this Z is consistent throughout ZA, ZB, and ZC, this is the most, this is the bottleneck usually in the PIP-based SNARKs. Usually it requires many rounds of interaction, and in the interactive setting, and in the non-interactive setting, it will lead to larger proof size. And also in circular-specific SNARKs like ROS16, this part link check is usually natively handled by the CRS, so and the AGM arguments. So there isn't such issue in circular-specific SNARKs like ROS16, Pinocchio, and stuff. But in a PIP-based SNARKs, we do suffer from this link check sub-PIP. Okay, so what do we do in our paper? We replace this link check. We argue that this link check wants us to prove that the prover knows Z such that ZA is equal to ZZ, and so on for the other proofs. So we kind of replace this check by a similar check on the polynomials. We say that if the left-hand side checks pass, the right-hand sides the right-hand side checks will also pass, and vice versa. So the right-hand side checks say that if we interpolate ZA as a polynomial and we get Z hat of A of X, it will be a linear combination of the polynomials interpolating the columns of the matrix A. And there are a bunch of coefficients, of course, because it's a linear combination. So we say that this link check can be translated into these coefficients being equal across these three lines of equations. So Z hat A, Z hat B, and Z hat C are all constructed with the same coefficients on different basis sets. Okay, and these basis sets are coming from the columns of the matrices A, B, and C. So same coefficients and all. We call this equifficiency check, by the way. So we kind of replace this expensive link check with our equifficient polynomial commitment scheme checks, which is with this equifficiency check. We call this equifficiency check, which is a made-up word. So we introduce a new tool, which is an EPC scheme. So first of all, let's formalize a bit the equifficient constraints. Equifficient constraints is a set of basis sets. It's like this calligraphic A, calligraphic B, calligraphic C, and all of these are separate basis sets. Like, for example, calligraphic A is just A1 through AN. All of them are basis polynomials. And we say that, for example, Z hat A, Z hat B, and Z hat C polynomials are said to satisfy this equifficient constraint if they can be expressed with the same coefficients across these three basis sets. Okay, so as you can see here, Z hat A, Z hat B, and Z hat C all have coefficients Z1 through Zn under different basis sets. So if this is satisfied, we say that these three polynomials are equifficient. Okay, this is just a definition. So an EPC scheme works just like a PC scheme. It has the same API, except one minor change. So the setup is exactly like a PC scheme. The maximum degree will be fed into the setup, and the setup will spit out public parameters PP. But there's this specialized algorithm that takes in the equifficient constraints and the public parameters, and it will output commitment key, verification key, and opening key. Okay, so this is the part that it will deviate from the normal PC schemes. And then everything goes through like usual PC schemes. The sender commits to a bunch of polynomials, sends a commitment to the receiver. Receiver wants to evaluate these polynomials on a random point. The sender actually evaluates those polynomials, sends and actually provides a proof of those evaluations, and sends the actual evaluations via the alongside with the proof to the receiver, and the receiver checks that those evaluations are correct according to that proof provided by the sender. And the specialized algorithm samples private randomness. This is a source of our SNARKs being having trusted setup. And also, these keys are constraint-specific keys. Like those ABC matrices that kind of form our basis sets are kind of encoded in the commitment key, verification key, and opening key. Okay, and the properties of our EPC schemes. So our properties are, again, very similar to the properties of PC schemes, except that there's one extra condition in a completeness, which says that if the prover actually knows a polynomial that the evaluation claims pass, and moreover, the prover knows these polynomials that satisfy the Equifficient constraints, then the proof should go through. Okay, the verifier should accept. And also, extractability has one extra condition. Not only the extracted polynomials have to satisfy the evaluation checks, like P1 of Z should be V1 through Pn of Z should be Vn, but also the Equifficient constraints should be satisfied on those polynomials, meaning that P1 through Pn should be Equifficient with respect to E. Okay, so these two extra conditions are padded to these normal PC properties. Okay, now our SNARK constructions. We devise the PIOP for a row check, which is very, very simple. It only requires to be sound. And then we compile it with EPC scheme. We get a preprocessing ZK-SNARK. Very simple. So we instantiate this generic construction in two regimes. One univariate regime, we get Pari, and the other multivariate regime, sum check based, we get Garuda. Okay, and our univariate EPC is based on KZG. It's a kind of we change a bunch of algorithm in KZG, and we get our univariate EPC, and we also tweak PST to get our multivariate EPC. Okay, this is how we get Pari and Garuda, which are instantiations of our generic constructions. Okay, and both unfortunately require circular-specific trusted setups. Okay, now let's go to the exciting part, which is the implementation and evaluations. Okay, so we implemented everything in our paper in ArcWorks. We implemented Garuda in a constraint system called GR1CS, or generalized R1CS, which allows us to express custom gates. GR1CS is exactly like CCS. It's not a novel contribution, but we found it much easier to work with. So we implement GR1CS. We added this in a recent PR to SNARK crate in ArcWorks. And then we kind of adapted all of the gadgets in ArcWorks to work with GR1CS. And then we implemented Garuda and Pari. And we also have an automatic solidity generator for Pari, meaning that you just specify the public input size, and it gives you a smart contract for that. So these are all implemented in Garuda Pari crate, in GitHub. Okay, so evaluation for Pari. As we discussed, Pari has the smallest proof size. In BN, the larger the security parameter gets, the advantage of Pari gets more clear. And also in BLS curves, we're always better. The proof size of Pari is constantly smaller than Gross 16 and Polymath, which are the other benchmarks. Okay, and we benchmark our circuits. We benchmark our proof systems on a circuit which is a repetition of a hash function. So we just implement this hash chain implemented by rescue hash function, and we use this as our benchmark circuit. And we see that in verification time, Pari is as fast as Polymath, okay, even slightly faster than Polymath. And because it doesn't require MSMs for public input, unlike Gross 16, it doesn't grow with increasing the input size like Gross 16. Okay, and in terms of gas costs, Pari and Polymath are kind of the same. Polymath is slightly better, but it might be because of not optimizing some things in solidity. I'm not a solidity expert, But you can see that Pari and Polymath are both much better than Flunk and Gross16 in terms of gas cost. And in terms of prover time, so you can see that Gross16 has a better prover time, but of course worse proof size. But Pari is much better than Polymath. Okay, so while it has a good verification time, it has a better prover time than Polymath. So more concretely, the verification time for Polymath and Pari are kind of 15% better than. I'm sorry. The verification time for Pari is kind of 15% better than Polymath, and for the prover time is 2x slower than Gross16, and but in comparison with Polymath, we're 30% faster. And just to advertise Pari, if you want to have a super succinct snark and the smallest proof size possible and a blazing fast verifier, and you want to avoid the proving overhead for Polymath, you better call Pari. Okay, now the evaluations for Garuda. So the same hash chain circuit. You can see that the verification time. So with comparison with Gross16, we're 2x slower in terms of verifier, but we're faster than all of the PIP-based SNARKs. Okay. In terms of proof size, we're almost less than 10 kilobytes. We're much smaller than the PIP-based SNARKs, but we're 2x smaller than the Polymath. And for the prover time, we're faster than all of the state-of-the-art, almost all of the state-of-the-art SNARKs out there with relatively small proof sizes. Okay. So just to advertise Garuda, again, if you want a ZK-SNARK with a fast prover that benefits from custom gates and free edition gates and has a small proof size, like under 10 kilobytes, and has a very fast verification, is 2 milliseconds, almost as fast as Gross16 and Pari and Polymath. And you want to use that as a drop-in replacement for Gross16. For example, you see that in these applications that went benchmarked Aptos and an Athor were much faster than Gross16. You better call Garuda. Okay, and some open questions. Can we have universal setups? Can we have post-quantum security? These are important open questions. And also, can we prove that Gross16's lower bound is tight? Meaning that can we design a SNARK in AGM that actually has two group elements? And also the other open question is that what are other applications of EPC schemes out there? Like can we accumulate EPC claims? Does it have any application in verifiable secret sharings and stuff? And yeah, that's it. This is the GitHub and ePrint address of Garuda and Pari. Thank you very much.
Thank you very much, Alireza. Thank you. So our next speaker will be Dimitris Kolonelos, who is currently a postdoc at Berkeley, and he will be presenting a talk regarding the doubly private smart contract. Dimitris, yeah, thank you, Anna.
Hey, hi from me, and thanks for the introduction and the invitation. I'm very excited to talk about our recent work with Sanjam Garg, Arushi Goel, and Rohit Sinha. So this is Jigsaw. We essentially introduce a new notion of privacy for smart contracts, something that we call doubly private smart contracts. And I'm gonna try, for the sake of this online science fair, I'm gonna try to keep things high level. I'm not gonna go into the very details of the actual scheme. So let me start. Yeah. So I guess everybody here is quite familiar with smart contracts. I'm not gonna introduce them formally. I'm gonna introduce them through a very simple example. Smart contract, the simple decentralized exchange. So So in this specific decentralized exchange example, we have two clients. One client comes and says, okay, I have 2 Bitcoins. I want to exchange them with Ethereum. And price 1 to 30 gives the data to the smart contract as an input. This is an input of the smart contract and leaves. And then at some point in the future, maybe in the long future, somebody else comes, another client comes and says, I have 70 Ethereum, I want to exchange them with Bitcoins in price 30 to 1. Gives this again as input to the smart contract. The smart contract now runs on the two inputs, identifies that there is a match between the intents, the orders of the clients, so executes the decentralized exchange and outputs the corresponding result of the decentralized exchange. And this is a transaction. So the transaction is consists of all the input data, output data, and the type of the smart contract that was executed. So all of this information goes on chain. And of course, it's no secret, it's something widely acknowledged that this is a very, very big privacy leakage because everything is stored on chain, everything is public. So any party, regardless of whether they are active participants of the blockchain or not, they can just go and observe the history of all the blockchain transactions, all the executions of the smart contracts. This is a very, very big privacy issue. Of course, it is well identified and a very popular approach to add privacy in smart contracts is ZK-SNARKs. This dates back to almost 10 years ago. The first idea came from Hawk in 2016. And the idea very simple is instead of executing the smart contract and put the execution on chain, you execute the smart contract locally, off chain, you put it in the ZK-SNARK prover, and the ZK-SNARK prover posts a ZK-SNARK proof that now serves as a transaction. This is a ZK-SNARK proof of correct execution of the smart contract. So this is sound. It says that the smart contract was executed correctly, and of course, cryptographically seals the transaction. Nobody can say what happened due to the ZK property, to the zero knowledge property. Nobody can say what happened in the transaction. Now, in this work, our main motivation is the following. We say that even though this proof is very, very good on chain, in the sense that it does not leak information about the transaction on chain, there still should be someone off chain that collects the data, executes the smart contract, and executes the smart contract, executes the prover of the zero knowledge of the ZK-SNARK, and posts the transaction on chain. And what we claim is that this is a non-affordable privacy leakage that we call off-chain privacy leak, that in many modern applications cannot be afforded, this privacy leakage. So in more conventional applications like payments, this can be okay because, for example, the two parties are trusted. One is sending some value, maybe buys something from the other entity. Maybe these parties are mutually trusted, so the sender can just compute the ZK-SNARK. But in modern applications, like for example in the space of decentralized finance, we claim that this cannot happen. Who can we put as a prover, as this trusted entity, for example, in trading or in auctions? This would give them a very, very direct front-running capability. And things are even worse in voting. Who can actually know the votes of all the clients? So we identify this off-chain privacy leak, and towards this, we introduced this notion of doubly private smart contracts. This is a definitional framework that for smart contracts that enjoy both on-chain and off-chain privacy, we construct doubly private smart contracts cryptographically, and our construction, we call it Jigsaw. We implemented Jigsaw and benchmarked it, and we also described meaningful applications. So for the rest of this talk, I'm going to give a very, very high level of Jigsaw. So let's say morally, what we do is to add yet another layer of privacy. So essentially, somehow philosophically, ZK-SNARKs are there in order to provide on-chain privacy, and then we add multi-party computation on top of zero knowledge, on top of ZK-SNARKs, in order to provide this off-chain privacy. So this is, let's say, somehow philosophically our approach. More concretely, Jigsaw can be thought of as an outsourcing mechanism in a privacy-preserving manner, of course, of a ZK-SNARK computation. So in this model, we envision that there are some parties, some dedicated parties that we call servers. There are some servers that are there just to provide privacy to the clients. They stand between the clients and the blockchain. And this cluster of servers forms something that we call the privacy provider service. So we envision this service as a service that is getting paid in order to provide off-chain privacy to the clients. So the scenario goes as follows. Oh, by the way, it's important to say that these servers have nothing to do with the consensus algorithm of the blockchain. They are completely independent from the validators, and they can definitely not interfere to the correctness of the transactions, to the consensus mechanism of the blockchain. They are independent parties. So the way that it goes is that the clients now are secret sharing their data, send them to the servers. The servers are executing a multi-party computation that outputs a transaction that is posted on chain. And this transaction is the traditional ZK-SNARK private transaction for an execution of a smart contract. And this can be thought of as essentially doing something around Zcash or Zexi, this architecture. But instead of having a single trusted entity to compute the ZK-SNARK, we have a cluster of servers, an MPC service. So this is the high-level idea of Jigsaw. The main question is, how do we actually do MPC for a ZK-SNARK prover? This sounds really outrageous. It should be something that gives the overhead of an MPC over the overhead of a ZK-SNARK. This sounds like something tremendously inefficient. But fortunately, in 2022, Ozdemir and Bonnet introduced this very, very elegant notion of collaborative ZK-SNARKs, which does exactly this. Each server knows only partially the witness, has a portion of the witness. This server is involved in a multi-party computation protocol, and at the end they post a proof for the whole witness, for the full witness. And of course, since this is a secure MPC, nobody gets to know the witness of the other servers. And this, the main point is that it is only with a minimal overhead, a very, very minimal overhead. So it's like 2 or 3 times worse than actually executing a ZK-SNARK computation, a ZK-SNARK prover. Okay, this is good enough, but we claim that if you take these collaborative ZK-SNARKs off the shelf and try to execute a privacy-preserving smart contract, this is just not gonna work. There are some efficiency limitations related to collaborative ZK-SNARKs. First, each server's computation is proportional to the full witness, not to the partial witness. So this is one problem, but more importantly, there is a very high communication overhead between the servers. Even if the computation is not that bad, communication, the latency is gonna affect a lot the computation time, the overall time to compute this proof. So for example, Poseidon hash is a very suitable hash function for traditional ZK-SNARKs. For collaborative ZK-SNARKs, it is not that suitable because it requires lots of communication. And according to our estimations, even very, very optimistic estimations say that collaborative ZK-SNARK for a moderate size Merkle tree is gonna cost around more than 2 minutes, which is prohibitive for blockchain transactions. So our main idea for Jigsaw, our core observation is that actually in the specific relation of private smart contracts, the bulk of the computation is actually involves only local data. So this this means that a great part of the computation of the ZK-SNARK can be actually computed by the clients themselves. So our main idea is that let each client compute a local ZK-SNARK for the part of the computation that they can actually do that is related to their data. And then they compute this proof, send it to the service, and then the service somehow complete the computation of the overall SNARK by computed via collaborative ZK-SNARK what is left. So somehow we split the computation between the local computation and the computation that absolutely needs the data of all the clients at the same time. And the final proof is the concatenation of all the local proofs and the collaborative ZK-SNARK proof. So this is a very simple idea and yet very, very effective, because after we saw that after a careful decomposition of the ZK-SNARK relation, actually the most expensive operations inside the ZK-SNARK, like all the cryptographic operations that we need to do for privacy-preserving smart contracts, like Merkle tree inclusions, commitment openings, PRF computations, all of these things can go to the local ZK-SNARK, which is very efficient, while the expensive part, the collaborative ZK-SNARK, is just left with minimal computation, essentially the execution of the function of the smart contract, and plus a few more field operations. So, and the good news is that the execution of this smart contract is in many cases extremely simple in reasonable applications, as for example in trading or atomic swaps, sealed bid auctions, lotteries, and votings. These are applications that we work in the paper and we actually saw and benchmark that they can be very, very efficiently implemented with double privacy via Jigsaw. Now, very, very quickly going to the implementation. For the sake of this talk, I will just give the punchlines, which is basically for the local ZK-SNARKs that are computed. Nothing surprising happens there. The time to compute this proof is more or less the time, I mean, it's like the cost is equivalent to a ZKAS or ZEXI. Computation, it's nothing surprising, around 1 and 4 seconds, let's say, in order to compute a local proof. The important part is the collaborative ZK-SNARK, which is actually it is seen as the overhead of the off-chain privacy. And for these applications that I described, atomic swaps, auctions, lotteries, and voting for reasonable number of participants, we saw that the proving time is not going to be more than 3 seconds. In some cases, it will be as low as 100 milliseconds, while in some other cases, it is about 3 seconds. And this is 40 to 50 times faster than actually using an off-the-shelf collaborative ZK-SNARK, where you put all the relation inside the collaborative ZK-SNARK. So this, essentially, this engineering of the relation of Jigsaw is giving you all of these improvements. So for the verification, the things are pretty straightforward. You just have to verify ZK-SNARK proofs, and it's the usual gas cost. I mean, so to conclude, the key takeaways are that first, the more elaborate the applications, the blockchain applications become, the more elaborate the privacy challenges become. We should, as cryptographers, come up with more elaborate ideas in order to achieve privacy. Applications are not just payments anymore, like 10 years ago or 15 years ago. We have much more these days. For example, we saw that off-chain privacy is essential. And the last point, as a cryptographer, I'm very, very excited to actually see that collaborative ZK-SNARKs can be practical. We think that they can play a very significant role in future applications. It's a very interesting concept, MPC for ZK-SNARKs. So try to use them. And we're very excited to see new applications of collaborative ZK-SNARKs. So thank you.
Thank you very much. So our next speaker will be Mahimna Kelkar. I'm sorry, I'm not familiar with non-French pronunciation. Who recently graduated from Cornell and is now a research scientist at Offline Labs. And he will be presenting a paper about breaking all our previous assumptions on key pairs in the crypto world.
Are my slides visible? Yes. Cool. So today I'm going to be talking about key encumbrance attacks, liquefaction, and complete knowledge. And thank you for the invitation. This talk is going to be based on two works, one presented at SBC last year and one to be presented at SBC this year. So the main starting point we have is actually many cryptographic protocols have these common intuitive goals. So usually there's a completeness-like goal which says an honest user, so this is someone who knows the key, will succeed in the protocol. And there's also a soundness-like goal which says that an adversary who doesn't know the key will fail. But what does it actually mean to know this key? So sort of the implicit model that we're working with is that Alice knows the key if she can explicitly furnish it as private input to the protocol. So for example, if the protocol says compute some function of the key in the input, then the typical mental model we have in mind is that Alice knows this key and this input locally, and then she computes this locally and then maybe uses it in the protocol to send it to another party. But as it turns out, there's a subtle discrepancy in this mental model, which, as I'll show, will lead to a new class of what I'll call encumbrance attacks. And this leads to new insights on the very definition of knowledge within cryptography. So the high-level idea is these encumbrance attacks will actually be breaking this mental model using trusted hardware or trusted execution environments, which are typically used to build secure protocols. So the high-level idea is here. On the left side, we have the protocol expectation is that the user controls her key locally. In a sense, the user has full access to her key. She can do everything that the key allows her to do. But what key encumbrance will do instead is that the key will be locked inside of this trusted hardware TEE box with a program that restricts or splits access to this key. In a sense, because the TEE is the only entity that controls this key, no external party sort of has full access to the key, and all of their access is just restricted based on this program. And as it turns out, this is what will cause problems in a bunch of applications, especially because existing techniques cannot distinguish between these two scenarios. So here's a very powerful, concrete new attack on blockchain-based voting. So typically in the setting, you can imagine a user who owns a key can do two things. So first is that she can spend the money in her wallet. And let's say she can also use this key to vote in a DAO voting proposal or a governance proposal based on how much cryptocurrency she has per se. Now, suppose that Alice is willing to be paid for her vote. She cares about her money, but she doesn't actually care for her vote. Now, she can't exactly just give her key to the briber because the briber can just steal Alice's money. But at the same time, the briber won't just give Alice the bribe in settings with private voting because there's no way for the briber to guarantee that Alice will vote according to his preference. Alice could just take the bribe and then just vote however she wants. But with key encumbrance, this leads to a sort of new mechanism for coordination between Alice and the briber as follows. So what Alice can do is she can willingly encumber her key and install a vote buying program given to it by the adversary, which will only allow voting for the adversary's choice. So at a high level, the key that Alice's wallet is controlled by will only exist inside of the TEE. It can be, for example, generated by the TEE itself. And then the program will still allow Alice to spend all of her money, so sign transactions that move money outside of the wallet. But specifically for this one governance proposal, it will only allow voting for whatever the bribing adversary's choice is. And this is kind of interesting because it leads to sort of this fair exchange between the user Alice and the briber for a vote for bribe fair exchange. And you can kind of see that Alice is okay with the bribe here because she only cares about access to her tokens and not her DAO vote. And the briber is okay with it because provably Alice can only vote for his choice and she can't just take the money and run. And as it turns out, that this actually breaks a long line of prior work on coercion-resistant voting, because all of these works make this implicit assumption that Alice has full access to her key at some point during the protocol, either during the registration phase, before the adversary comes into the picture, or after the adversary is gone, in a sense, to allow revoting. But in all these cases, there's this implicit assumption that gets broken with these TE-based encumbrance. And you can do actually something even more general than this, is create what we'll call a dark DAO, which is a hidden marketplace to anonymously connect voters and bribers. So on one side of the market, you have voters who want to sell their voting power. And on the other side, you have bribers who want to buy this voting power. And you can connect them without them needing to know each other, and in a completely hidden way from the governance protocol. And in fact, we wrote a recent paper on all kinds of shenanigans that you'll do this, which we called Liquefaction, and specifically on privately liquefying blockchain assets. And this is the paper that my co-author James Austin will present at SBC, so be on the lookout for that. So the core idea here is that there's this single entity address ownership assumption that's pervasive in a lot of blockchain protocols. What this means is that one private key has only one owner. So this is kind of a natural assumption to make, because everywhere you're told that don't share your private key. If you share your private key, then someone can just steal your funds. So it's sort of this natural assumption to make that one private key will only be held by one owner. But the problem is that encumbrance breaks this, because if the key is inside of a trusted hardware and the program is such that it can split access to multiple users, then this can create problems for many applications. So we implemented this liquefaction through a rich program policy engine for how this access control happens between different participants. So you can think about this program as implemented as a private smart contract, which we did so on this TE blockchain called Oasis. Oasis is only used here for sort of liveness of the TE, but for all modeling purposes, you can just think about this as a single TE as well. And you can kind of think about how changes to this access control can be made, and we defined an expressive policy engine for how access control is defined and how it can change with time. As one very simple example, you can think about, let's say, an Ethereum address that controls 10 ETH. And now typically applications will think that this address is controlled by a single person. It's an EOA address. So it's controlled by a single person, and that person is 10 ETH. But what liquefaction can allow you to do is actually split this account into basically sub-accounts with their own separate balances. So here, Alice can have 5 ETH, Bob can have 2 ETH, and Carol can have 3 ETH, in a way that parties don't need to trust each other at all. They don't need to know each other, and they can't take each other's balances in their own sub-accounts. And this sort of access control is completely hidden from the main blockchain called Ethereum. Ethereum still thinks that it's just a single owner who has 10 ETH. This is another cool sort of prototype that we built, which is called Take My Ape. And I really encourage you to look at this demo for this. So basically the idea is we actually bought an ape for this demo, and we can allow you to create an encumbered account. So an account where the key is held inside this trusted hardware. And we will send you this ape to this encumbered account. And the program in this account will be such that you can prove that you actually own this ape, but you won't be able to transfer or sell it. And you can do this for basically the cost of just a couple dollars, versus the cost of this ape is tens of thousands of dollars. And you can, doing so, you can actually get access to really cool exclusive things like the Bored Ape Yacht Club Discord channel, for example, or members-only areas on their website, because you can still prove ownership. And in fact, from the chain's perspective, you are actually the owner because only you can prove access to this Bored Ape for that limited amount of time. And in general, we show that there's a lot of powerful attacks that you can do within and beyond blockchains as well. Things like breaking deniability and deniable end-to-end encrypted messaging, or even severing the soul of soul-bound blockchain tokens, or transferring non-transferable cryptographic proofs. All kinds of shenanigans like wash trading or faking theft, more private hidden privacy pools, or being able to rent account credentials, reputations, things like that. And these are sort of very seemingly unrelated attacks that are made possible through this key encumbrance, but we unify them by identifying a problem with how cryptography defines knowledge. And we propose this new primitive called proofs of complete knowledge. So to kind of understand at a high level the root cause of these encumbrance attacks, coming back to the previous slide, you can kind of think about the protocol expectation as the key is held locally by the user, but on the key encumbrance side, the key is held inside of this trusted hardware box. So on the left, you can think about the user knowing the key in some sense, but on the right, nobody knows the key. But as it turns out, proof of knowledge protocols, which is the standard technique to prove knowledge of the secret key, can be executed even when the TE controls the key. And this is sort of this mismatch that allows for these encumbrance attacks to take place. So here's sort of the subtle insufficiency that we found in the proofs of knowledge primitive with this context of encumbrance attacks. So at a high level, this proof of knowledge is this interactive protocol where a prover wants to convince a verifier, let's say as an example, that she knows the secret key corresponding to some public key. Now, typically it satisfies its completeness, which says that an honest prover can convince the honest verifier. And there's a knowledge soundness part, which formalizes this knowledge part in the proofs of knowledge, which says that if some prover, even an adversarial one, convinces the honest verifier, then an efficient extractor machine can sort of recover the secret key by interacting with the prover. And this sort of makes sense from a knowledge definition standpoint, because if this extractor can recover it from the prover must have known it in the first place. But in fact, this is sort of where the problem lies, and this gap between theory and practice comes into play. And the problem here is that the extractor is really a theoretical proof construct, and sometimes it can't even be run in practice, even given an arbitrary amount of time, because of things that exist outside of the model. So for example, if the key is held inside of trusted hardware, then by assumption that the trusted hardware is secure, you can't have the extractor extract some information from the hardware. And this leads to our new primitive, which we call proofs of complete knowledge. And this was in a work at CCS last year and also presented at SBC last year if you want to go take a look at that talk. And the core idea here is we actually instantiate this extractor as a physical entity rather than just it being a theoretical proof construct. So here's sort of the high-level design of what a proof of complete knowledge is. So you can think back to the proof of knowledge in the same way we have a prover and a verifier, but we have this new sort of resource entity that the prover can use in a way that an honest prover will only use approved resources. An adversary can, of course, use unapproved resources, but we make hardware assumptions that they will only use practical resources. So we can define a set of what resources are practical, which is larger than the set of approved honest resources, and the adversary can use any one of them. And now what we'll do is this extractor, instead of being a theoretical proof construct, will actually be the physical wire that connects the prover to the resource. And we'll design our complete knowledge protocols in a way that will force the reveal of the witness to this extraction channel. And because this is sort of in the prover's domain, if it's leaked on this physical channel to the resource, the prover can tap this channel and learn the secret herself. So this kind of gets rid of any sort of encumbrance based on TEs. In a sense, the prover can only convince the verifier of a proof of complete knowledge if it has unencumbered access to the secret key. And just to kind of take it back to our vote bribery example, if the voting platform, instead of requesting a proof of knowledge when trying to vote, actually requests a proof of complete knowledge, then it will only be accepted when Alice knows her key herself and it's not locked inside of these encumbered accounts held inside of a TE. So what this means is that Alice can't just sell access to her vote without also losing access to the funds in her wallet, which is exactly the thing we wanted in the first place. So to summarize, I talked about these new encumbrance attacks, basically that work by locking the key inside of a trusted hardware. And this breaks the commonly held belief that one key has only one owner. And this creates a bunch of problems for many blockchain applications, among others. And I also talked about this new complete knowledge primitive, which, as it turns out, is necessary to prevent this new class of encumbrance attacks. I'll end there. I have a link to the two papers I talked about, the complete knowledge paper, which was at CCS last year, also presented at SBC, and the liquefaction paper, which appeared at S&P 2025 and will be presented at SBC next week as well. Thank you. I think.
Sorry. Thank you very much, Mahimna. So I was just saying, we now have a dozen minutes to discuss and cross-pollinate for all our presentations. So I shall encourage everyone to ask any relevant question about the other presentation. And I would like to go first. So if I understand correctly, Mahimna, the whole scheme that the whole nefarious scheme that you exposed is based around the presence of a TEE, where an intermediate program could actually behave in a way that is not desirable for the people running the blockchain. Are there similar threats in other cryptographic schemes that do not involve a TEE?
So I would say this is not sort of an attack on TEs. This is actually attackers using secure TEs.
Yes, exactly. But what I mean is that this is an attack that requires to have a TEE in the loop.
Right. So you could do the same sort of attack with an MPC as well, but TEs give you this sort of trusted third party essentially for free. And so they make a lot of these coordination problems between MPC go away. So coordination that you require to make MPC protocols, they sort of go away. So from a liveness standpoint, TEs are better coordination tools for these attacks to happen. And there's a lot of protocols in general on blockchains that are now putting a large amount of money in TEs. And our kind of point there is there's a lot of secure protocols now built using TEs. And we show that attackers can use TEs themselves to attack other protocols as well. And we should be mindful and try to understand the nuances of this more.
And in the end, the more surface you expose, the more attacks you will be vulnerable to. I see. Thank you very much. Dimitris, is there any comment you would like to raise?
Hi. Yeah, it's very exciting work. I mean, all of the talks that I heard. Any comment or question? I'm not sure. I'm not. Maybe. I'm not sure because I think that I was familiar with the works already before joining. But I think it's very the work of Garuda and Pari is very interesting because essentially what is happening there is somehow that if I understand correctly, you circumvent the growth 16 lower bound, but in the sense of concrete proof size, but not in the sense of theoretical proof size, right? Because I'm trying to say that you circumvent the concrete growth 16 lower bound, but not the theoretical one, right? Because you still have, in theory, more elements in the proof, right? So it's a matter of moving elements from G2 to G1. Is this a correct? You still have four elements.
Yeah, sure. So I don't know. So the proof size is usually but yes, it has a mathematical format of like n group elements and like m field elements or whatever. But yeah, at the end of the day, it's just the concrete size that matters, right? And
I know. I mean, it's a great
yeah.
work, and it's actually very nice that somehow
Yeah.
you circumvent the theoretical barriers in practice.
But
Because
the most important barrier is not circumvented, so which is the Gross's lower bound, and which says that the proof has to be two group elements. So we recently had a work on by Yuval and Gal, I guess, which has one group, well, which is designated verifier with just one group element, and that's designated verifier. But with the public verifiability, it is very interesting to work on, like to see whether the bound on Gross's paper is tight. Actually, it's been many years. Like it was 2016, and yet we don't have any evidence of having like two group element SNARKs. Yeah, that's, and of course these are all group-based constructions. It is very interesting to see how we can extend them to, for example, to lattice-based constructions. Yeah, I see that more feasible than hash-based construction, because you have to somehow. So all of these constructions like somehow depend on obfuscating some kind of challenge in the SRS, and that's kind of doable with lattices, not with hash-based constructions. I don't know. I encourage people to work on this. I'm working on this, and yep.
Yeah, I had another question, Dimitris. Actually, I was wondering, to go back to your own work. Suppose I already have a contract that is deployed, right? What would it entail it as a company or a developer to convert it to use the Jigsaw protocol? Would it be, what would the process look like?
Is this smart contract a private smart contract or like a usual
No,
smart
let's go
contract
with a
without any
very basic, no privacy smart contract, and I would like to integrate your scheme because, well, for all of the reasons that you mentioned. What would be on the high level the steps to follow?
Because I want to add that there are layers of privacy here, because maybe you have a private smart contract that is not doubly private smart contract. So there is no privacy at all. There is the Zexi/Aleo solution that adds privacy, but again, somebody has to take the data and perform the computation. And then, so if you want to somehow jump from the non-private at all to private, you first need to go through the architecture of Zexi. You need to formalize your smart contract in terms of records, in terms of in terms of all of these privacy preserving architecture. You should first go through the architecture of Zexi. So this is the first layer. The second layer, going from Zexi to doubly private smart contracts, I think it's not going to be that challenging. So for the most part, you have to follow the pattern that we follow in order to split the relation. This is a zero knowledge, a ZK-SNARK engineer. I believe the most difficult part is to integrate your smart contract into the privacy preserving smart contract architecture. That's, let's say, the most challenging part, which is, it's, I mean, it depends. If we are talking about theoretically, I would say that it's easy. But if you go to deploy, I mean, if you try to deploy things, it's always.
Yes, of course, the devil is in the details, but there is no like major conceptual issues that should arise. I was wondering, maybe that's a very naive perspective, but I'm under the impression that the MPC network, I mean, a server could be a vulnerability in the whole mechanism. Like, are they non-attack that could hamper the safety of the system on these servers?
So
because you have in some way something that is looking to both the clients on the chain, right? And of course, that's like a very obvious single point of failure. So yeah, I was wondering, what are the attacks that you can expect here?
So That's a very, very good question. It's something that I didn't mention because I wanted to keep things high level, but there is an absolutely necessary property that we demand in the Jigsaw in doubly private smart contracts, that is integrity, essentially correctness of smart contracts should be as secure as it is in every privacy preserving smart contract solution. So these servers, even if they all collude, even if they want to absolutely perform an attack, they shouldn't be able to do so. And then the reason that they are not able to do so is because they post a ZK-SNARK that is at the end gonna be verified. It's gonna be a correct ZK-SNARK, right? So as long as this ZK-SNARK is correct, is verified, then this means that the transaction is secure. They cannot actually do anything related to integrity. What they can actually do
And
is
there is
they
no way for them to leak information on the
That's
partial
another story.
ZK-SNARKs.
So the privacy is another thing. So the security that we support is we need one honest server. So as long as you have all but one, even if you have all but one servers that collude and that are malicious, they cannot learn any information. This has to do with additive secret sharing, essentially. So even if one server is honest, then the privacy is guaranteed. Of course, if all servers collude, then they will learn the information.
Of course, but I suppose that this is an attack that is, So yeah,
that's
so
the cryptographic. That's the cryptographic guarantees of the.
Okay, that makes sense. Thank you very much. Alireza, is there any comment that you would like to share?
All the works were good, amazing. I mean, I guess, actually, I was in one of Mahimna's talks in Penn, so very familiar with that. But this Jigsaw was recently out, and I have a question about this work. So currently, you kind of split the witness of your computation to a bunch of servers, do a collaborative snark, and then return the result to the on-chain thing, return the proof on the on-chain. So the functionality itself that you're calling, like the function endpoint that you're calling, is still visible to the servers, right?
That's very yeah. That's correct. We do not support function hiding.
I see, and I suppose that that's not easy to solve, right? Because it requires obfuscation. Like it's
in theory, can you not have a single function that calls other functions in the smart contract? So you just always access that one function, and then that will internally call the actual function you want to call.
Oh yeah, beautiful.
There are various solutions that we thought about, None of it was gonna be like efficient enough so that it's worth it. I mean, another solution is to even secret share the function itself. So instead of secret sharing the data, you also secret share the function of the smart contract. So no single server gets to learn the representation of the function, and somehow it's treated inside the MPC. This is not going to be efficient. I mean, all of these ideas are theoretical. So at the end, we said that maybe it's a trade-off that we have to take at this point. It's a very nice, I mean, it's one of the, I don't know, top list future work considerations. It's a very interesting problem.
Yeah, and I also had some questions about dynamic snarks. I guess Babis is not around, right? So I was curious about this recent papers on 3 PCPs, where you can like incrementally change the PCP string, and with this dynamic, I guess dynamic snarks change the witness. They don't increment the witness. Like they don't make the witness larger, just change a bunch of bits in the. So if it's a PCP based snark, you just change some bits of the PCP. But yeah, 3 PCPs, I guess they're incomparable with dynamics. So yeah, I was going to ask that from Babis.
Yeah, but from what I remember from the paper, you're right. They are only changing they cannot change the size of the thing. So, which is why it was actually used in the coprocessor, because when you change the let's say a ZK encoded SQL query, you still have the same dimension for everything involved. So there is no actual modification in the size of the PCP, improve the witness or whatever. So yeah.
I see.
But by the way, Alireza, sorry, yeah, please go on.
No, that's good.
Okay. Yeah, I had a question for you. So you are using the R1CS on the generalized R1CS constraint system. Is it like a hard requirement of your schemes, or could you work, for instance, with AIR or Plonkish system constraint systems?
Good question. So for the generic construction, where we kind of decouple this linear, this linear check and the nonlinear checks. Well, so say we want to use Plonkish constraints. So this linear check would kind of be like the analogous of the linear check in Plonkish is the permutation check, I guess. Like you have to kind of design a PCS that also supports a permutation arguments. I don't know. That's not that is not clear to me how we can extend this to other constraint systems, because our argument still holds in Plonkish. Plonkish also has two PIOPs that one is very expensive, which is the permutation arguments, and the other one is just simple nonlinear checks. So this argument still holds in Plonkish world. However, it is not clear to me that how we can kind of port this expensive argument, like kind of push this responsibility to the cryptographic world instead of the information theoretic world. Not sure.
Gotcha, that makes sense. Perfect.
Yeah.
Does anyone has any other question or comment that they would like to raise?
Yeah, I actually had one question about Jigsaw. So if I understood correctly, the secret sharing is done in an n out of n fashion. So you have n servers, and the witness for the ZK-SNARK is stored n out of n secret sharing. But from a liveness perspective, have you thought about how to make like the t out of n sharing efficient, or if you know if there's any bottlenecks for that?
In principle, there are various MPC and secret sharing protocols that can work generically for the collaborative ZK-SNARK. So they're gonna give you different efficiencies, last security guarantees, and liveness guarantees, and so on and so forth. In our case, we just say take some secret sharing with these security properties. It's a cryptographic work, and you're gonna get this, let's say, an instantiation of Jigsaw with these security guarantees. I like the additive secret sharing. Myself, I like the additive secret sharing because it gives you these very, very high privacy guarantees. In general, you can also use honest majority, or other MPC protocols also work for collaborative ZK-SNARKs. It's quite the technique. This goes back actually to Ozdemir and Bonnet. It's quite generic the way that they compute the MPC prover inside. The ZK-SNARK prover inside an MPC. And but the very, very let's say details of liveness, for example, we don't have guaranteed output delivery. That's something that there's no collaborative ZK-SNARK that gives guaranteed output delivery. That's a very important open problem, not only for smart contracts, but in general for collaborative ZK-SNARK. It's a very nice thing that but yeah, in our case, we said this is the proof of concept. This is a starting point, and then if you want to look at the, let's say, details, some properties, this is gonna go to, I don't know, follow-up works. In general, collaborative ZK-SNARKs have a lot. I mean, we believe that they have a lot of potential in both research and practical deployment. So many open problems there, really.
So can I ask something? Yeah, so in collaborative SNARK, there's this assumption that these proving nodes, they don't know each other's witness, like they cannot. So is it like an MIP setting, like multi-interactive proof setting, or they can have information about each other's witness?
It's irrelevant. We say that of course, if they have information about others' witnesses, the protocol is gonna be easier to construct. Let's say, how can I put it? It's gonna be more convenient for the actual construction, but it's we consider that these servers are somehow adversarial to each other, so they shouldn't know. They shouldn't know in the sense that they should not learn. The main property that we want to achieve is that they should not learn the witness of they are mutually distrustful parties.
I see.
So that's the main goal, that there should be such a protocol so that I am not learning the witnesses of the others. If they actually know the witness of that's irrelevant. That's irrelevant. It's actually a relaxation, an easier.
I see. So because in MIPs, like, okay, if the provers don't know each other's share of witnesses, they're more restrictive. Like they have less power, essentially. So the soundness analysis might be easier. Like the verifier has more power, essentially, right? It's like an MIP setting. Like, but I guess enforcing that the provers don't know each other's witness portion is the main thing. I don't know. Is the main.
Let's say there is something that is you have the power of interaction in collaborative ZK-SNARK. In MIPs, you have the server. I'm sorry, the verifier that communicates with all the provers, but the provers do not communicate with each other, right?
Exactly.
It's a different model. While in this case, you have interaction. These are a lot of rounds of interaction. It's actually linear in the size of the witness.
Between the servers.
Between the servers, linear in the multiplication depth in more detail. They are proportional to the multiplication depth of the circuit. It's a lot of interaction. So that's why you can actually achieve this, and it's somehow you have much more power than MIPs. In MIPs, you cannot interact with each other, right?
Yeah, I see. So it's simply just MPCing the prover, like
precisely 100%.
Okay.
Perfect. So I think that we run out of our allocated time span. So I would like to thank you again, all of you, for all your presentation and the discussion, the very enriching discussion afterwards. And see you at SBC'25. And best of luck with the pursuing of your work. Thank you.
Thanks.